On June 14, 2026, the Large Hadron Collider recorded its final physics collisions before a 4-year upgrade. In CERN's control rooms, the last event displays from ALICE, ATLAS, CMS, and LHCb. But the machine was not stopping because physics had run out of questions. The standard model still leaves gravity, dark matter, the origin of neutrino masses, and the cosmic matter-antimatter imbalance unresolved, while years of searches have made many of the simplest answers harder to place. Tonight, we can follow those disappearing possibilities and ask where the missing physics could still be hiding. For more than a decade, the Large Hadron Collider has sent beams of protons around a circular tunnel under the French-Swiss border region, bringing them together inside enormous detectors and recording what comes out. The collisions are small enough to vanish before the eye could ever see them, but the detectors surrounding those collision points are built to notice the traces left behind, the curved paths of charged particles, the showers of energy, and the small imbalances that can suggest that something invisible carried momentum away. The famous success came early. In 2012, the ATLAS and CMS experiments announced the discovery of the Higgs boson, the particle associated with the field that helps explain why many elementary particles have mass. That discovery completed a missing part of the standard model, the theory physicists use to describe the known elementary particles and 3 of the 4 fundamental interactions. It was a remarkable confirmation of an idea that had been waiting for experimental proof for decades. The collider kept running, and that part is easy to overlook. The Higgs discovery did not turn the Large Hadron Collider into a finished project. It made the unanswered questions more precise. Once the missing particle predicted by the standard model had appeared where it was supposed to, physicists could look more carefully for things the standard model did not predict: heavier particles, rare decays, unusual imbalances, or tiny differences between measurements and calculations that might point toward a deeper description of nature. The expectation was never that one particular new particle had to appear on a particular afternoon. Particle physics does not work with that kind of schedule. Still, there were good reasons to search. The standard model is extraordinarily successful inside its domain, but it is not a complete account of the universe. Gravity does not fit inside it. Dark matter is not explained by it. The imbalance between matter and antimatter in the universe is not explained by the amount of asymmetry contained in the model. Even neutrino masses tell us that the simplest version of the standard model cannot be the final description. So there is a peculiar situation underneath the French and Swiss countryside. Physicists have a theory that works with astonishing precision, and they also know that it leaves some of the largest facts in nature outside its reach. That tension is the real subject of our story. The interesting part is not that CERN has failed to produce some dramatic object that tears physics apart. That would be a much simpler story. The more subtle story is what happens when a machine keeps looking, keeps measuring, keeps becoming more sensitive, and the missing pieces remain difficult to see. A search can return without the particle it hoped to find, but that does not leave the experiment where it started. Imagine looking for an island across a dark sea. If you can only see a few kilometers from shore, then an empty horizon tells you very little. If you later build an instrument that can see much farther and the horizon is still empty, the island may still exist, but it can no longer be hiding in the part of the sea you have already examined. The absence has acquired information. Particle physics does something similar, although the map is not made of kilometers. It can be made of possible masses, possible lifetimes, possible interaction strengths, and possible ways a new particle might decay. Each experiment covers only part of that map. When a search becomes sensitive enough to detect a particular kind of signal and does not find it, physicists can begin ruling out that region for that particular model. This is why the long quieting of the collider in 2026 matters. The LHC is not being abandoned. CERN has entered what it calls Long Shutdown 3, a major period of maintenance and reconstruction that will transform the machine toward the high-luminosity Large Hadron Collider. Selected sections of the existing accelerator are being dismantled and replaced with new systems. The goal is not to make the ring vastly larger. The tunnel remains where it is. The goal is to create far more useful collisions over time, giving the experiments a better chance of seeing processes that happen so rarely that the present data may contain only a few examples, or none at all. There is something almost restful about that strategy. When nature does not answer loudly, you do not necessarily shout a more dramatic question. Sometimes you ask the same question with greater patience. That patience has shaped the LHC from the beginning. The detectors do not wait for a new particle to announce itself. They reconstruct events from fragments. They compare enormous collections of collisions with detailed predictions. They look for patterns that occur slightly too often, slightly too rarely, or with a shape that does not quite match what the standard model expects. And when a hint appears, the experiment enters the slower work of discovery, with more data, more calibration, independent checks, alternative explanations, and often the realization that the hint was a statistical fluctuation or an imperfect calculation rather than a new law of nature. That can sound disappointing if we imagine science as a sequence of revelations. But a theory that survives a harder test has told us something. A possible signal that disappears after better measurements has told us something too. The space of explanations becomes smaller, and the next question becomes more focused than the one before it. By the time the LHC stopped producing physics collisions in June of 2026, CERN could point to a record amount of data and thousands of scientific results. Yet the deepest problems that motivated searches beyond the standard model were still there. Dark matter had not been identified as a new LHC particle. Gravity had not been brought into the standard model. The cosmic preference for matter over antimatter remained unexplained. The known particles continued, for the most part, to behave with an almost inconvenient loyalty to the equations already written for them. And so the tunnel enters its long period of reconstruction with a curious kind of success behind it. The machine has found what nature allowed it to find, and in many searches it has also learned where certain hoped-for answers are becoming harder to place. That gives us a different way to think about the unknown. We often picture discovery as a light appearing in darkness, a new particle, a new object, a clear signal where there was none before. But there is another kind of discovery that happens more slowly. You begin with an enormous field of possibilities. You test one region, then another. Some ideas survive. Others lose the places where they could have hidden. The unanswered region remains, with boundaries defined by the tests already completed. As the collider grows quiet beneath the ground, the question worth keeping nearby is this. If physicists already know that the standard model cannot be the whole story, why has it been so difficult to make the missing part reveal itself? The question becomes easier to hold once we look at the theory itself, because the standard model is not a rough sketch of particle physics. It is the framework that has survived decades of experimental tests, often with a precision that makes its missing pieces feel almost paradoxical. The name can sound modest. A standard model might suggest something provisional, a useful approximation waiting to be replaced. But in particle physics, the theory grew from ideas and experiments stretching back through much of the 20th century. By the early 1970s, its modern structure had come together. Since then, accelerator after accelerator has tested it, and particle after particle has appeared where the theory said it should. At its simplest, the model begins with two families of matter particles, quarks and leptons. There are 6 quarks and 6 leptons, arranged in 3 generations. The ordinary matter around you is built mostly from the first generation. Up and down quarks form the protons and neutrons inside atomic nuclei, while electrons occupy the space around those nuclei. The heavier generations exist as well, but they are unstable, and they tend to decay into lighter particles. Then there are the particles associated with forces. Photons carry the electromagnetic interaction. Gluons belong to the strong interaction that binds quarks together. The W and Z bosons carry the weak interaction, which is involved in forms of radioactive decay and in the reactions that allow stars to shine. The Higgs field, with its Higgs boson, supplies another part of the structure by helping explain how several elementary particles acquire mass. That is already enough machinery to describe an extraordinary amount of the visible world. It explains why atoms can exist, why nuclei hold together, why unstable particles decay, why light interacts with charged matter, and why the particles produced inside accelerators appear in particular combinations and at particular rates. Physicists can use the theory to calculate the probability of very specific processes, and experiments can compare those calculations with what their detectors actually record. Again and again, the comparison works, and that success is especially important because the tests are not all repetitions of the same experiment. Different particles are produced in different ways, at different energies, inside different detectors, and their decays can be measured through many independent channels. A small disagreement in one place may disappear when more data arrive, while agreement in another place can become precise enough to constrain ideas that once had plenty of room to survive. The Higgs boson itself is a useful example. Its discovery did not merely add one more name to a particle chart. After the particle was found, ATLAS and CMS could begin measuring how it interacts with other particles and comparing those interactions with the pattern predicted by the standard model. The question shifted from whether the Higgs existed to whether it behaved like the Higgs the theory expected. That shift from existence to precision is one of the defining features of modern collider physics. Once the obvious pieces are in place, physicists use repeated measurements to test whether the same underlying description continues to hold. A tiny, persistent disagreement can matter, but so can the disappearance of one. This is why the problem is more interesting than saying that our theory is wrong. A theory can be incomplete without being useless, and this framework is the clearest example. Within the territory it describes, it works so well that any deeper theory will have to contain a reason for that success. Whatever eventually extends, it cannot erase the standard model. At familiar energies, it will have to reproduce the results that experiments have already measured. And yet there are things the model does not contain. Gravity is the most familiar omission. The standard model describes the electromagnetic, strong and weak interactions, but not gravity. For an individual particle in a collider, gravity is so weak compared with the other forces that physicists can usually ignore it without spoiling their calculations. Across planets, stars and galaxies, of course, gravity becomes impossible to ignore. General relativity describes that larger gravitational world extremely well, but combining gravity with the quantum framework used for particle physics remains an unresolved problem. So our two most successful descriptions of nature live beside one another without fitting comfortably into a single complete theory. Dark matter creates another absence. Astronomical observations tell us that galaxies and larger cosmic structures behave as though there is far more gravitating matter than the ordinary atoms we can see. The standard model contains no established particle that naturally accounts for all of that dark matter. This is one reason collider physicists have searched for new particles that might pass through detectors without leaving the ordinary kinds of tracks. But dark matter is not obliged to reveal itself in a proton collider. It may interact too weakly. It may be too heavy. It may be something that does not fit the simplest particle candidates at all. The important point here is narrower. The standard model by itself does not tell us what the dark matter of the universe is. Antimatter creates another gap. For every known matter particle, nature provides a corresponding antiparticle. In the early universe, our best picture suggests that matter and antimatter were produced in nearly equal amounts. If the balance had remained perfectly even, matter and antimatter would have largely annihilated each other as the universe cooled. Yet the world around us is made overwhelmingly from matter. The standard model does include a real difference between the behavior of matter and antimatter, known as CP violation. Experiments have measured it, but the amount supplied by the known standard model mechanisms is not enough to explain the enormous cosmic imbalance we observe. Something about the early universe still appears to be missing from the account. Neutrinos offer an even quieter clue, and there are three known types of neutrino associated with the electron, muon, and tau. For a long time, the simplest form of the standard model treated neutrinos as massless. But experiments discovered that neutrinos can change from one type into another as they travel, a phenomenon called neutrino oscillation. That behavior requires differences between neutrino masses, which means the old massless picture cannot be the final one. The adjustment sounds small because neutrino masses are tiny, but conceptually it matters. Nature had already told us, outside the original framework, that the framework needed more. None of these problems tells physicists exactly what comes next. Gravity does not hand us a new particle with a known mass. Dark matter does not arrive with instructions for how strongly it should interact inside ATLAS or CMS. The matter-antimatter imbalance does not identify the missing source of asymmetry. Neutrino masses do not by themselves tell us which deeper mechanism gives those masses their particular values. This is what makes the search beyond the standard model unusually difficult. There is strong evidence that the present description is incomplete, but that evidence does not point toward one unavoidable extension that the LHC must discover. For a while, several elegant possibilities seemed especially attractive. Supersymmetry, for example, proposed a new partner particle for each known particle and offered ways to address several theoretical problems at once. Other models introduced additional Higgs particles, new force carriers, hidden sectors, or candidates for dark matter. Some versions placed new particles within the energy range that the LHC could explore. Those ideas gave experiments concrete things to look for. But a concrete prediction creates a concrete risk. If a model says that a particular kind of particle should appear within a certain range of masses and with a certain pattern of interactions, then enough data can test that claim. The detector may see the pattern, or it may not. And when it does not, the scientific result is not that every version of the idea has vanished. Usually the conclusion is much more careful. A particular region of possibilities has become inconsistent with the observations, given the assumptions of that search. The surviving theory has to move elsewhere. That careful narrowing is easy to miss when we talk about discovery, as though it always means adding something new to a list. Physics can also advance by subtraction, and the standard model sits at the center of this process. It keeps surviving measurements that were designed in part to expose its limits. Each survival strengthens our confidence in the territory where it works, while the unanswered questions beyond that territory remain exactly as real as before. So the puzzle becomes sharper because we are not waiting for evidence that our present theory is incomplete. We already have that evidence in gravity, dark matter, neutrino masses, and the unexplained dominance of matter. What we are waiting for is a bridge between those large unanswered questions and something an experiment can measure directly. And that brings us to one of the least intuitive ideas in modern particle physics. If an experiment looks for that bridge and finds no new particle at all, how can the absence itself become a measurement? Imagine that you are searching for a new particle, but you do not know exactly where it is. You know only that, if it exists in a certain range of masses and interacts strongly enough with the particles you can produce, then your detector should leave a recognizable pattern in the data. That is enough to begin. The first step is to describe the signal you hope to see. A new particle may decay into known particles, or it may escape the detector and leave behind an imbalance in momentum. It may produce several jets of particles, a pair of leptons, photons, or some rarer combination. The details depend on the model being tested, but the logic is always similar. You start by asking what the detector would record if the new process were real. Then you ask a second question that is just as important. What ordinary processes could imitate that same pattern? This is the background, and particle collisions are crowded. Even when nothing new is happening, the standard model can produce complicated events that look surprisingly similar to the thing you are searching for. A detector may see missing momentum because a neutrino passed through without being measured directly. It may see jets because quarks and gluons were produced in an ordinary interaction. It may see a pair of leptons because a familiar boson decayed in a familiar way. So physicists cannot look at an unusual event and declare that something new has appeared. They have to understand how often the known physics should produce similar events, how the detector responds, and how much uncertainty remains in both the measurement and the prediction. This is why modern particle searches usually work with large collections of events rather than a single dramatic collision. Suppose a model predicts that over the amount of data collected, a new particle should create a noticeable excess in a particular region of the measurements. The experiment counts the events there. It compares them with the background expected from known processes. If the number is larger than expected, that may be interesting. But it is only the beginning. Random fluctuations occur naturally, so if you repeat enough measurements, some bins in some distributions will be high and others will be low. A small excess can appear by chance, detector calibrations can shift, a background estimate can improve, and more data can smooth out what once looked unusual. The task is to decide whether the difference is large enough, stable enough, and unlikely enough under the standard model to justify a stronger conclusion. Discovery is the part everyone remembers, but most searches end instead with limits. A limit is a way of saying that, if a particular model were true in a particular region of its possible settings, the experiment should probably have seen something by now. Because the expected signal did not appear, that region becomes difficult to reconcile with the data. The word region matters because a search does not usually eliminate an entire idea in one stroke. The same theory may allow a light particle or a heavy one, a short-lived particle or a long-lived one, a strong interaction or a weak one. These possibilities can be represented on a kind of map. One axis may show mass. Another may show interaction strength. In some searches, the axes represent the masses of two different hypothetical particles. In others, they may describe lifetime, decay probability, or another property. Before the experiment, a large part of that map may be open. After the experiment, some of it may be shaded away. That shading is one of the quietest products of a particle collider and one of the most important. If you look at scientific plots from Atlas or CMS, you will often see curves dividing the page into regions that are excluded and regions that are still allowed. To someone unfamiliar with the language, the plot can look almost disappointingly empty. There is no photograph of a new particle. There is only a boundary. But the boundary contains information. It says that a certain combination of mass and interaction strength no longer fits comfortably with what the experiment observed, under the assumptions used in that analysis. Another experiment may test a different region. A later analysis may use more data, better reconstruction, or a new strategy and push the boundary farther. The possible home of the particle becomes smaller. This is the basic meaning of an exclusion limit. There is a statistical language behind those boundaries, and it is worth understanding slowly, because the words can sound more absolute than they really are. Physicists often quote limits using a confidence level, commonly 95%. That does not mean there is a 95% probability that the theory is false, and it does not mean there is only a 5% chance that a particle is hiding in the excluded region. The exact interpretation depends on the statistical method being used. What the number does provide is a consistent rule for deciding which parameter values are sufficiently incompatible with the observed data, given the model, the estimated backgrounds, and the uncertainties built into the analysis. The important lesson is not the technical definition. It is the conditional nature of the statement. The experiment is saying something like this. If this model behaves in this particular way, and if the particle has properties in this particular range, then the data we collected do not support that possibility. Change the model and the map can change. Change the assumed decay and the map can change. Allow the particle to live much longer or interact much more weakly, and the search may no longer be sensitive to it at all. This is one reason headlines about particle physics can become misleading so easily. A paper may exclude a large region of a simplified supersymmetric model, while a summary outside the field turns that into the claim that supersymmetry has been disproved. Those are not the same statement. The experiment has not searched every possible version of an idea. It has searched the versions that produce signals the detector can recognize with the available collision energy, luminosity, reconstruction methods, and analysis strategy. And yet this does not make the result weak. Science becomes useful when its statements are precise enough to fail under specific conditions. A broad idea that can survive any possible outcome teaches us very little. A model that predicts what should appear in a defined region can be confronted by data, and if the prediction does not survive, the map changes. That is the sense in which an absence can become a measurement. There is another subtlety here. A null result can become more constraining even when the collider energy stays almost the same. Imagine a rare process that happens only occasionally in the collisions you can already produce. A much larger useful dataset gives the experiment more chances to see that process. Better detectors can also identify events that older reconstruction methods missed. Improved algorithms can separate signal from background more cleanly. A search can become sensitive to weaker effects by becoming more patient and more precise. That is part of the logic behind the high-luminosity LHC. The upgraded machine will not turn the current collider into something unrecognizable overnight. Its great advantage is the amount of data it is designed to deliver over time. More collisions mean larger samples of familiar processes, but they also mean better access to rare ones. Measurements of known particles can become sharper. Searches for faint deviations can probe regions that are currently too difficult to distinguish from background. This matters because new physics does not owe us a spectacular signal. If it exists close enough to the reach of the collider, it may announce itself through a particle produced often enough to stand out quickly. But it could also appear as a tiny change in a decay rate, a small distortion in a distribution, an unusual lifetime, or a process so rare that years of data are needed before the pattern becomes visible. And if none of those patterns appears, the absence continues to redraw the map. There is something almost opposite to intuition in this. We tend to imagine that a larger scientific instrument gives us more things to see. Often it does. But one of its deepest powers is that it gives us more ways to say where something cannot be. That sounds negative only if discovery is defined as the arrival of a new object. For a physicist trying to understand nature, narrowing the field can be just as real. Every excluded region removes one version of the story. Every measurement that agrees with the standard model makes certain alternatives harder to maintain. Every disappearing anomaly teaches researchers to be more careful about the remaining ones. Over time, the remaining parameter space becomes more constrained. And once you understand that, one of the most discussed ideas in modern particle physics looks different. For years, supersymmetry offered physicists a large and elegant family of possible new particles. Some versions placed those particles close enough to the LHC that the collider had a real chance to find them. The particles did not appear where many of the simplest searches expected them, so the story continued through the boundaries those searches could move. The boundaries moved, and supersymmetry is a useful place to watch that happen, because few ideas in modern particle physics have spent so long living in the space between mathematical elegance and experimental silence. Supersymmetry begins with a proposal that sounds almost extravagant. For every known particle in the standard model, the theory introduces a related partner with a different kind of quantum spin. Quarks would have partners called squarks, electrons would have selectrons, and the particles associated with the Higgs field would have partners called Higgsinos. The exact particle content depends on the version of the theory, but the general idea creates a second layer of particles lying beyond the ones we already know. The attraction was never merely that a larger particle catalog would be interesting. Supersymmetry could soften a difficult question about why the Higgs boson is as light as it is compared with much higher energy scales. In some versions, the lightest supersymmetric particle could also be stable, electrically neutral, and difficult to detect, giving physicists a possible candidate for dark matter. There were several problems a single framework seemed capable of touching at once, which made supersymmetry unusually appealing. But appealing is not the same as confirmed. When the Large Hadron Collider began exploring energies beyond those reached by earlier accelerators, physicists searched for many forms of supersymmetric particles. Some of the simplest possibilities would have produced fairly obvious signatures. Heavy new particles could be created in proton collisions and then decay through a chain of lighter supersymmetric states, ending with something invisible that escaped the detector. In that case, the event might contain energetic jets or leptons, together with an imbalance in transverse momentum, suggesting that an unseen particle had carried some of the momentum away. Those searches became increasingly sensitive, but no confirmed supersymmetric particle appeared. Supersymmetry remained viable in regions that were harder to see, so researchers shifted their attention toward them. One of those regions involves what physicists call a compressed spectrum. The phrase means that two or more hypothetical particles have masses that lie close together. When a heavier supersymmetric particle decays into a slightly lighter one, very little energy is available to the visible particles produced in the decay. This creates an experimental problem because detectors such as ATLAS are extraordinarily capable, but they still have thresholds. A high-energy electron is easier to identify than a very low-energy one. A long-charged particle track is easier to reconstruct than a trail consisting of only a few hits in the innermost detector layers. A decay that releases large amounts of visible energy can stand above the background more clearly than one that leaves only a faint trace. So a compressed spectrum gives hypothetical particles somewhere quieter to hide. In March of 2026, ATLAS presented new searches designed specifically to reach deeper into this difficult region. One focused on compressed Higgsino-like states, particles related to the supersymmetric partners of the Higgs field. In these models, Higgsinos mix to form neutrinos and charginos, and when their masses are close together, their decays can produce extremely soft, low-momentum particles. Earlier searches had difficulty seeing some of those tracks. The new analysis used machine learning techniques designed to recognize them at lower momenta. One part of the search looked for a heavier neutralino decaying into the lightest neutralino together with two low-momentum leptons. A lepton is a particle such as an electron or a muon. When the mass difference is small, one of those leptons can carry so little momentum that ordinary identification methods may miss it. ATLAS therefore trained new algorithms to search for track patterns that could still reveal the decay. The observed data agreed with the standard model, so no Higgsino signal appeared, but the result reached into regions that had remained difficult for the LHC, and in parts of the parameter space, moved beyond long-standing limits set by CERN's Large Hadron Collider. The improvement was concrete enough to compare with older machines. In one of the compressed Higgsino searches, ATLAS excluded some scenarios with chargino masses reaching about 132 gigaelectronvolts, when the mass difference was around 1.8 gigaelectronvolts. A complementary displaced track analysis reached higher masses for a smaller splitting, extending the previous ATLAS boundary and passing the old LEP limits across the mass-splitting region it targeted. Those numbers are not universal limits on Higgsinos. They belong to the particular model assumptions behind the analysis, which is exactly why the plot matters more than a single headline number. The boundary bends because the experiment is more sensitive in some combinations of mass and mass difference than in others. The disappearing track search told the same story in a different pair of coordinates. There, ATLAS mapped chargino mass against lifetime. The new techniques allowed the collaboration to test particles that would leave only 3 or 4 hits before decaying, far shorter traces than standard tracking normally uses. ATLAS excluded chargito masses up to 225 gigaelectronvolts for lifetimes below 0.03 nanoseconds, and up to 720 gigaelectronvolts for a lifetime of 1 nanosecond. Again, the important feature was not the largest number at the edge of the plot. It was that a previously difficult region had become experimentally visible enough to test. That is what a boundary moving looks like. There was no new object to photograph, yet a set of possible Higgsino masses and mass differences became harder to maintain. Another search followed an even stranger signature, a charged particle track that appears to stop inside the detector. Some supersymmetric models contain a chargino that lives long enough to travel a short distance before decaying into an invisible neutralino and a very low-energy pion. If the chargino is charged while it travels, it can leave hits in the tracking detector. Then it decays, and because the neutralino escapes unseen while the pion can be difficult to reconstruct, the track seems to disappear. The challenge is that a very short track contains very little information. Standard reconstruction methods normally rely on a larger number of detector hits. Atlas developed algorithms capable of identifying tracks using only a few of the innermost measurements, and combined them with techniques that could recover very soft pions. Again, the point was to make the detector sensitive to a place where the signal could have been hiding. No convincing supersymmetric signal appeared, so the result instead placed tighter limits on the possible masses and lifetimes of the charginos described by the models being tested. For some combinations of lifetime and mass, the allowed region retreated. For other combinations, the search had less power, and those possibilities remained open. This is why it is misleading to say that the LHC searched for supersymmetry and failed. Supersymmetry is not one particle with one mass and one predictable decay. It is a broad theoretical framework containing many possible spectra, lifetimes, interactions, and signatures. What the experiments can do is confront particular versions with increasingly precise observations. The easier regions are usually searched first, and when nothing appears there, experimentalists develop methods for dimmer signatures so the boundary can move again. This process can continue for years, and it produces a peculiar relationship between theory and experiment. Constraining the easiest versions leaves a theoretical framework with fewer parameter choices, and each new exclusion asks the surviving models to occupy a more specific part of the map. Sometimes that leads theorists toward versions that are less simple than the original motivation suggested. Sometimes it points experimenters toward signatures nobody prioritized before, such as long-lived particles, displaced decays, or tracks that vanish after only a short distance. And sometimes it changes how the field thinks about what the next discovery might look like. A new particle does not have to arrive as a clean bump in a graph. It might travel farther than expected before decaying. It might produce particles too soft for older searches. It might interact so weakly that only a tiny fraction of events contain a recognizable trace. The search strategies expand because the remaining territory is different from the territory already explored. There is an important humility built into this. A limit does not tell us that nature must have chosen one of the regions left unshaded. Nature is free to ignore the whole framework. Supersymmetry may describe part of reality, or a version of it may exist at energies far beyond the LHC, or nature may have taken a completely different route. The experiments cannot choose among those possibilities by preference. They can only continue asking questions that produce measurable consequences. By the spring of 2026, Atlas could say that some of its new supersymmetry searches had reached places that had resisted earlier analyses, including compressed Higgsino scenarios where the visible decay products carry very little energy. The result was not a discovery of the particles. It was a more detailed description of where particular versions of them could no longer comfortably live. That is a quieter achievement than the appearance of the Higgs boson, but it has a different value. The surviving models therefore have less experimental freedom than before, and supersymmetry is only one example. There is another way the map can change that feels even stranger, because sometimes an experiment does not merely fail to find a predicted new particle. Sometimes it sees a small disagreement with the standard model, enough to make physicists wonder whether the long-awaited crack has finally appeared. Then more data arrive, calculations improve, the measurement becomes sharper, and the apparent crack can begin to close. A boundary can move because a search sees nothing where a new particle might have appeared. There is another way our picture of the unknown can change, and it is more delicate. Sometimes an experiment does see a difference, small enough to require caution, but persistent enough to attract attention. Different measurements may begin pointing in a similar direction, and for a while the possibility of new physics starts to take shape in the data. Then the measurement becomes better, and the shape changes. One of the clearest examples came from an experiment called LHCb, built to study particles containing beauty quarks. Beauty quarks are unstable. They survive for only a tiny fraction of a second before transforming into other particles, but the details of those transformations can be measured with extraordinary care. Rare decays are particularly useful because they can be sensitive to effects from particles that are too heavy to be produced directly. A new particle does not always need to appear as a visible object inside a detector. Quantum processes can allow its influence to alter how often a known particle decays in one way rather than another. If the effect is real and the measurements become precise enough, the disagreement can appear indirectly. LHCb spent years examining a family of rare decays involving B mesons, particles that contain a beauty quark. Some of the most closely watched measurements compared decays that produced electrons with otherwise similar decays that produced muons. Electrons and muons are different particles, but within the standard model, they belong to the same larger family called leptons. The muon is much heavier. Once that mass difference is properly accounted for, however, the forces described by the standard model should treat the two flavors in the same way. This principle is known as lepton flavor universality. The comparison gives physicists a fairly clean question. Do B mesons decay into electrons and muons at the relative rates the standard model predicts? For several years, the answer looked slightly uncomfortable. Measurements from LHCb, along with related results elsewhere, produced a pattern of tensions that became known as the flavor anomalies. One LHCb result announced in March of 2021 attracted particular attention. The collaboration compared a rare B meson decay involving muons with the corresponding decay involving electrons and found a value that differed from the standard model expectation, with a statistical significance of about 3.1 standard deviations. 3.1 standard deviations was interesting, but it was not enough for particle physicists to claim a discovery. The result attracted attention partly because it did not stand alone. Other measurements involving beauty particles had also shown tensions, and theorists could construct new particles or interactions that might influence several of them together. For a while, one possible explanation was that electrons and muons were not being treated quite as universally as the standard model required. An unseen interaction might have been changing the probabilities of these rare decays, giving physicists an indirect route toward new physics without requiring a completely new particle to appear in the detector. But the evidence still needed to survive a better measurement. LHCb returned to the question using the complete datasets from the first two LHC runs and a more comprehensive analysis. Two related B meson decay modes were studied simultaneously. The measurements were performed across two different regions of the relevant particle mass, producing 4 comparisons. The researchers also improved their treatment of background processes that can imitate electron decays, one of the technically difficult parts of the analysis. When the new result was presented at CERN in December of 2022, the earlier tension had not grown stronger. The measurements were in excellent agreement with lepton flavor universality, and the newer analysis superseded the earlier comparisons. That word superseded is useful here. The older measurement was not removed from the scientific record. It remains part of the history of the experiment, together with the uncertainties and methods available at the time. But once a broader analysis uses more complete data and improved techniques, the newer result becomes the better description of what the experiment has learned. Nothing about this makes the earlier work pointless. The previous measurement had been a real result obtained from real data, and LHCb had never presented its 3.1 standard deviation tension as a discovery. More data and stronger control of the analysis were exactly what the situation required. When those arrived, the interpretation changed. This is part of the ordinary rhythm of precision physics. An anomaly can be worth investigating even if it later fades. The important question is whether it survives when the measurement becomes more demanding. A second example involves one of the best-known particles in the standard model, the W boson. The W boson helps carry the weak interaction, and its mass is connected through the standard model to other precisely measured quantities, including the Higgs boson and the top quark. Physicists can therefore compare direct measurements of the W mass with the value expected from the wider structure of the theory. For years, measurements from different experiments were broadly compatible with that picture. Then, in 2022, the CDF experiment at Fermilab reported an exceptionally precise value for the W mass that was substantially higher than the standard model prediction and inconsistent with several earlier measurements. CDF was not an LHC experiment. It had operated at the Tevatron Collider in the United States, which had already shut down. But the measurement immediately mattered to particle physicists everywhere, because a persistent disagreement in the W mass could point towards something missing from the standard model. Other measurements therefore became even more informative. Atlas revisited its own analysis and published an improved W mass result in 2023 that remained compatible with the standard model. Then CMS added an independent LHC measurement. In September of 2024, CMS announced its first measurement of the W boson mass using proton collision data from the LHC's second run. The result was about 80,360.2 million electron volts, with an uncertainty of 9.9 million electron volts. What matters for our story is where that measurement landed. It agreed with the standard model prediction and with the other measurements considered by CERN, apart from the unusually high CDF result. The disagreement did not disappear completely. The CDF measurement still exists, and understanding why it differs remains a legitimate scientific question. But the wider collection of measurements became more difficult to interpret as a simple signal that the standard model had failed. Near the edge of what we know, this distinction matters. When a small discrepancy appears, physicists do not immediately need an explanation involving a new particle. First, they need to know whether the discrepancy survives. Different experiments use different detectors, collision environments, analysis methods, and sources of uncertainty. If the same effect remains visible across those differences, confidence in it can grow. If it does not, the map changes again. This is slower than the popular image of discovery, where one decisive observation suddenly reveals a hidden part of nature. Precision measurements often accumulate for years. Values shift as uncertainties shrink. Calculations improve. Different experiments disagree for a while, and then sometimes move closer together. That slow process is one reason physicists can place so much weight on the discoveries that eventually survive it. The LHCb flavor measurements and the W boson mass measurements are different cases, and they should remain separate. One concerns rare beauty particle decays and lepton universality. The other concerns a fundamental property of the W boson, and the unusual CDF value remains part of an unresolved comparison. What they share is the way science responds to tension. A deviation becomes interesting enough to test more carefully. New data and improved methods make the question harder. Then the amount of room available for the dramatic interpretation either survives or becomes smaller. This gives us another way to understand the long search beyond the standard model. The absence of a new particle is one kind of silence. Another arrives when a measurement that once looked unusual moves back toward the familiar theory as the experiment becomes more precise. That silence contains information too, because every anomaly that fades removes one more relatively simple route through which deeper physics might have revealed itself. The unanswered problems are still waiting. Dark matter remains unexplained. The cosmic dominance of matter over antimatter remains unexplained. Neutrino masses still require an extension beyond the simplest form of the standard model, and gravity remains outside its quantum framework. So the puzzle has become more specific. The standard model cannot be the whole description of nature, yet some of the obvious new particles have not appeared, and several much discussed tensions have become less compelling after better measurements. The missing physics may therefore be hiding in places that are harder to reach. And there are several very different ways that could happen. There are several possible hiding places for the missing physics, and one reason physicists take them seriously is that the evidence for incompleteness does not come only from particle colliders. It also comes from the universe itself. If every search at CERN had agreed perfectly with the standard model, and if the standard model also explained everything we observed in the sky, the long absence of new particles might eventually begin to look like an answer. Perhaps the theory would be complete. But that is not the situation we live in. Look far beyond the underground ring near Geneva, and the same theory that works so beautifully inside a detector begins leaving important questions unanswered. The clearest of these may be dark matter. Dark matter was not invented because a collider produced a mysterious invisible particle. The problem developed from astronomical observations. Galaxies contain stars and gas that move under gravity, and when astronomers measure those motions, the visible matter does not appear to provide enough gravitational pull to explain what they see. The evidence became especially persuasive as different observations began pointing toward the same general conclusion. Stars orbit within galaxies in ways that imply more mass than the luminous material can account for. Galaxy clusters behave as though they contain large amounts of unseen mass. Light from distant objects bends as it passes massive clusters, allowing astronomers to map gravity through an effect called gravitational lensing. Those maps again indicate more mass than can be found in the visible stars and gas. One of the most famous examples is the Bullet cluster, where two galaxy clusters have passed through one another. The hot ordinary gas, visible in X-rays, does not occupy the same regions as most of the mass inferred through gravitational lensing. The separation is difficult to explain if all of the gravity comes only from the ordinary matter we can see. Something seems to be contributing gravity without behaving like ordinary luminous matter. We call that unknown component dark matter. The name describes our ignorance more than our understanding. We can infer that something is there from its gravitational effects, but we still do not know its composition. It could consist of one new kind of particle. It could involve several. The relevant particles might be light, heavy, or somewhere in between. They might interact with ordinary matter through mechanisms so weak that direct encounters are extremely rare. Some proposals could potentially produce signals at colliders, while others would be much more difficult for the LHC to reach. This distinction is important. When an LHC search fails to find one proposed dark matter particle, it does not make the astronomical evidence disappear. The galaxies continue to move as they do. Gravitational lensing still maps more mass than the visible material accounts for, and galaxy clusters continue to show the same missing gravity problem. A collider search can close one possible explanation without closing the underlying question. That is a very different kind of mystery from an anomaly inside a detector. The mystery exists whether CERN finds the answer or not. Neutrinos carry a separate clue, and they pass through ordinary matter with remarkable ease. Vast numbers of them can move through Earth without interacting with anything at all, which makes them difficult to study, but also gives them unusual importance in particle physics. For years, the simplest form of the Standard Model treated neutrinos as massless. Then, experiments studying neutrinos from the Sun and from Earth's atmosphere discovered something that did not fit that picture. Neutrinos produced in one type could later be detected as another type. An electron neutrino could effectively become a muon neutrino or a tau neutrino as it traveled. This phenomenon is called neutrino oscillation. For oscillation to happen in the way experiments observed, the neutrino states must have different masses. The discovery was important enough that the 2015 Nobel Prize in Physics was awarded for the experimental work demonstrating neutrino oscillations and showing that neutrinos have mass. The masses are extremely small, but the conceptual consequence is not. The original Standard Model did not provide those masses in its simplest formulation. Again, nature was telling us that the description had to extend beyond the framework that worked so well everywhere else. But once again, nature did not tell us exactly how to extend it. There are multiple ways to introduce neutrino masses into a broader theory. Some involve additional neutrino states. Some connect to mechanisms operating at energy scales far above what current colliders can directly explore. Some could be related to other unresolved questions, including the early history of matter and antimatter. The experimental fact points beyond the old model without providing a single road leading there, and gravity leaves a separate gap. Gravity is so familiar that it is easy to forget how unusual its position is in fundamental physics. We feel it constantly. It shapes planets and stars, bends light, governs the motion of galaxies, and helps determine the large-scale evolution of the universe. General relativity describes gravity with extraordinary success by treating it as the geometry of space-time. Particle physics uses a different language. The Standard Model is a quantum theory that describes particles and interactions using quantum fields, and the electromagnetic, weak and strong forces fit within that framework while gravity does not. For ordinary LHC collisions, this is rarely a practical problem because gravity between individual elementary particles is extraordinarily weak compared with the other interactions. Physicists can calculate what happens in a proton collision without needing quantum gravity to describe the detector event. But conceptually, the separation remains. We have general relativity for gravity and the quantum framework of particle physics for the other interactions, and we do not yet possess an experimentally confirmed theory that joins them into one complete description under all conditions. The Standard Model therefore cannot be declared complete because the LHC has not found an obvious replacement for it. The observations do not allow that conclusion because dark matter remains outside the known particle inventory. Neutrino masses require physics beyond the simplest Standard Model. Gravity remains outside its description of quantum interactions. And the imbalance between matter and antimatter gives us another unanswered question, one that reaches back almost to the beginning of the universe. Matter and antimatter are closely related. For a matter particle, nature provides a corresponding antiparticle. When a particle meets its antiparticle under the right conditions, they can annihilate, converting their mass into other forms of energy. In the hot early universe, matter and antimatter should have been produced in nearly equal amounts according to our best understanding. Yet nearly everything around us now is matter. The atoms in your body are matter. Earth is matter. The sun and the stars we observe are overwhelmingly matter. Large regions of ordinary antimatter are not seen filling the universe in a matching abundance. Some asymmetry must have allowed a small excess of matter to survive. The Standard Model contains a real mechanism that distinguishes matter from antimatter in certain processes. It is called CP violation, and experiments have measured it repeatedly. So the theory is not perfectly symmetric between the two. The problem is the size, because the known sources of CP violation within the Standard Model are not sufficient to explain the enormous matter dominance of the present universe. Something about that early imbalance is still missing. Here the collider measurements meet the cosmic evidence. Inside CERN, experiments search for new particles and tiny deviations from predicted behavior. Outside CERN, the universe provides evidence that the present theory cannot account for everything we observe. Those two facts have to be true at the same time. The missing physics cannot merely solve a mathematical inconvenience. Whatever deeper description eventually succeeds must also remain compatible with the enormous body of measurements that the Standard Model already gets right. Any deeper explanation must also survive the searches that have already found nothing, which changes what that experimental silence can mean. At first, it is tempting to say that the LHC has failed to reveal the answer. But every exclusion limit, every precision measurement, and every anomaly that becomes smaller removes some of the easier ways that the known cosmic mysteries could have connected to collider physics. Dark matter is still there, but many specific particle candidates have less room than they once did. Neutrinos still have mass, but the mechanism producing those masses has not revealed itself as an obvious new LHC particle. The universe still prefers matter, but the extra source of asymmetry required to explain that preference remains unknown. Gravity still refuses to fit inside the Standard Model, while the particle interactions measured at accessible energies continue to agree remarkably well with it. So the situation is more constrained than it first appears. We know there is something beyond the current framework, because nature has already shown us problems the framework does not solve. At the same time, experiments have spent years removing some of the simplest places where that something might have been hiding. The unknown has not vanished. It has been pushed into a more complicated landscape of possibilities. And one of the most revealing places to see that tension is antimatter, because physicists have been able to take one of the strangest substances we can make, hold it long enough to study it, and ask a question that once sounded almost impossible. If you release antimatter in Earth's gravitational field, which way does it fall? Antimatter seems, at first, like it should provide exactly the kind of doorway physicists have been looking for. It is familiar enough to belong inside established physics, yet different enough from ordinary matter to invite a simple question. If some hidden law treats matter and antimatter differently, perhaps that difference could explain why almost everything we see in the universe is made of matter. By this point, the tension has shifted. The universe already gives us several reasons to expect physics beyond the simplest standard model, while each better experiment removes another easy way of connecting those cosmic clues to a measurable signal. The missing explanation remains, but its experimental paths are becoming narrower. The difficulty is that every careful test has to separate a genuine difference from the strange circumstances required to study antimatter at all. Ordinary hydrogen is easy to find. A hydrogen atom contains a proton and an electron, and hydrogen is the most abundant element in the universe. Antihydrogen is its antimatter counterpart. It contains a negatively charged antiproton with a positively charged positron around it. On paper, the two atoms should have matching properties under the fundamental symmetries built into modern physics. In practice, comparing them is remarkably difficult because antihydrogen cannot be placed in an ordinary container. If an antihydrogen atom touches normal matter, the particles and antiparticles can annihilate. So CERN's antimatter factory has to create antiprotons, slow them down, combine them with positrons, form neutral antihydrogen atoms, and then hold those atoms away from the walls of the apparatus using magnetic fields. Only after all of that can an experiment begin asking what sounds like an elementary question. What happens if you let one go? Gravity should pull antimatter downward. General relativity does not give antimatter a special permission to fall upward, and the equivalence principle at the heart of Einstein's theory gives physicists good reasons to expect that matter and antimatter respond to gravity in the same basic way. But until recently, the gravitational motion of neutral antimatter had never been observed directly. The challenge is easy to appreciate if you imagine trying to measure the fall of something that cannot touch your measuring equipment. The Alpha collaboration approached the problem with an apparatus called Alpha G. It trapped antihydrogen atoms vertically and then gradually weakened the magnetic fields holding them. Once released, some antihydrogen atoms escaped through the top of the trap and others through the bottom. They eventually touched normal matter and annihilated, allowing detectors surrounding the apparatus to record where those annihilations occurred. Gravity creates a small preference, because if the atoms respond to Earth's gravity in the familiar way, more of them should leave through the bottom than through the top. Alpha repeated the release process under carefully controlled conditions and compared the observations with computer simulations. In September of 2023, the collaboration reported the result. Within the precision of the experiment, antihydrogen behaved consistently with the ordinary attractive gravitational force of Earth, which means the observed fall was downward. The measurement was not infinitely precise. Alpha reported sensitivity at roughly 20% of Earth's gravitational acceleration, so there was still room for smaller differences that future experiments could examine. But one dramatic possibility had become much harder to entertain. Antimatter did not appear to fall upward. That is an important result precisely because the more surprising result would have changed so much. If antihydrogen had responded to gravity in a radically different direction from hydrogen, physicists would have needed to reconsider some very deep assumptions about gravity and fundamental symmetry. Instead, the first direct observation behaved much more normally, while the larger antimatter mystery remained. Alpha continued testing it in other ways. Hydrogen atoms have a set of precisely measurable energy levels. Their internal structure responds to electromagnetic interactions, and spectroscopy can measure tiny separations between those levels. If antihydrogen differs from hydrogen in a way forbidden by our current understanding, careful comparisons of the two could eventually reveal it. In May of 2026, Alpha announced a major improvement in one of those comparisons. The collaboration measured a tiny feature called the ground state hyperfine splitting of antihydrogen. This splitting comes from the magnetic interaction between the antiproton and the positron inside the anti-atom. hydrogen's equivalent transition has been measured with extraordinary precision. The electromagnetic radiation associated with it is connected to the famous 21-centimeter hydrogen line used throughout radio astronomy. For antihydrogen, the measurement is far harder. Alpha's earlier measurement from 2017 had reached a precision of about 400 parts per million. By 2026, improvements in the experiment allowed the collaboration to reach roughly 4 parts per million. That was a 100-fold improvement, and once again the result did not reveal an obvious disagreement with ordinary hydrogen. This is the pattern that has followed antimatter through many precision tests. Physicists keep finding better ways to compare matter and antimatter, and the comparisons keep becoming more demanding. A large unexplained difference would be extremely important. So far, the expected symmetries have survived these particular tests. But this does not mean matter and antimatter behave identically in every respect, because a measured asymmetry called CP violation already shows that they do not. The letters refer to two transformations. Charge conjugation exchanges particles with antiparticles. Parity can be thought of as reversing spatial coordinates, similar to reflecting a process in a mirror. For certain weak interactions, nature does not remain perfectly unchanged when both transformations are applied together. Matter and antimatter can decay at slightly different rates. That difference is real, and it was first established in neutral kaons in the 20th century and has since been observed in several types of mesons. The standard model includes a mechanism that produces CP violation through the way quarks mix with one another. Physicists therefore do not need to invent a matter-antimatter difference, because they have measured one. The problem is that the known effect is too small to account for the universe around us. That is why new examples of CP violation are so carefully studied. For a long time, confirmed CP violation had been observed in mesons, particles built from a quark and an antiquark, while baryons contain 3 quarks and form a different family of particles. Protons and neutrons, the familiar particles inside atomic nuclei, are baryons. Finding CP violation in baryon decays would therefore extend the phenomenon into another major family of matter particles. LHCb had been searching for that effect for years. Earlier analyses produced intriguing evidence in some baryon decays, but the statistical case was not yet strong enough to establish an observation. Then the collaboration combined large datasets from the first 2 runs of the Large Hadron Collider and examined decays of a particle known as the bottom lambda baryon. The experiment compared how the baryon decayed with how its antimatter counterpart decayed. In March of 2025, LHCb reported that the difference had crossed the threshold particle physicists use for an observation. The statistical significance exceeded 5 standard deviations. For the first time, CP violation had been observed in the decay of a baryon. The result matters because baryons make up the ordinary matter around us. It shows that the asymmetry between matter and antimatter is not confined to the meson systems where it had previously been established. And yet it does not solve the cosmic mystery. The observed effect remains compatible with the standard model. The known sources of CP violation in that model are still far too small to explain why the visible universe ended up with such an overwhelming abundance of matter. Antimatter, therefore, gives us an unusually clear example of the problem facing modern fundamental physics. A direct gravitational test becomes possible, and antihydrogen falls downward within current precision, while spectroscopic comparisons improve by 2 orders of magnitude without revealing a forbidden difference. A new type of CP violation is finally observed in baryons, but the effect fits within a theory that still cannot generate enough asymmetry to explain the cosmos. Each result teaches us something real without yet providing the missing bridge. If these quiet questions are helping you settle into the night, you can subscribe and find another one whenever you are ready. This does not make the experiments unsuccessful. Their value comes from making the question more precise. If antimatter had fallen upward, an enormous theoretical door would have opened. That door now looks much narrower. If antihydrogen spectroscopy had revealed a large forbidden difference, another route beyond current physics would have appeared. At the precision reached so far, it has not. If baryon CP violation had been far larger than the standard model could accommodate, it might have offered a clue toward the matter-dominated universe. Instead, the first observation has extended our knowledge of a known asymmetry without making it large enough to solve the larger problem. And the larger problem remains. Somewhere in the early history of the universe, conditions allowed matter to survive when an almost balanced mixture of matter and antimatter might otherwise have left very little ordinary material behind. Without that small preference, there would be no stars made from matter, no rocky planets, and no atoms lying in a room listening to a story about where those atoms came from. We know the imbalance happened because we are living inside its consequence. What we do not know is which piece of fundamental physics made the imbalance large enough. The answer may involve particles too heavy for current colliders to produce, interactions so weak that they rarely leave a measurable trace, unusual signatures that experiments have only recently learned how to recognize, or a mechanism that a proton collider was never going to reveal directly. By now, those possibilities are no longer equally easy places to search, because years of measurements have already begun shaping the territory and changing the question with it. If the missing physics really exists, but it has avoided direct searches, precision tests, and some of the most obvious antimatter clues, where can it still hide? There are at least 4 broad ways a deeper theory could remain out of view, and none of them requires the standard model to suddenly fail in an obvious collision. The first possibility is that the new particles are too heavy. A collider can only create particles if enough energy is available in the collision. The Large Hadron Collider accelerates protons to enormous energies, but the energy carried by each proton is shared among smaller constituents inside it, mainly quarks and gluons. The actual interaction that produces a new particle happens between those constituents, so the energy available for that particular event varies from collision to collision. If a hypothetical particle is heavier than the energy available in the relevant interaction, the LHC cannot produce it directly. More data do not solve that problem in the same way they help with a rare process. You can collect more collisions and become much better at finding something that is rare but accessible. You cannot create a particle whose production requires an energy you never reach. This is one reason the absence of a new particle at the LHC does not imply that no such particle exists anywhere in nature. A theory might place the new physics just beyond the collider's reach, or many orders of magnitude beyond it. In the second case, the LHC could operate perfectly for decades and never create the particle directly. The possibility is important because some of the unanswered problems we have been discussing do not tell us the scale at which their solution must appear. Neutrino masses may be connected to particles much heavier than anything current accelerators can produce. A deeper theory of gravity may become important at energies so remote from the LHC that direct production is not a realistic expectation. Even supersymmetry, if nature uses it at all, is not required to place its particles conveniently inside today's accelerator range. This is the simplest hiding place to imagine. There is one complication. Particles too heavy to create directly can sometimes still influence lower energy measurements indirectly through small changes in probabilities and decay patterns. That is why precision experiments remain useful, even when direct production is impossible. But indirect effects can be subtle, and they do not guarantee that the underlying particle can be identified uniquely. The answer may be farther up the energy scale. The second possibility is almost the opposite. The particles may be light enough to produce, but they may interact so weakly with ordinary matter that the main detectors rarely notice them. Neutrinos already show us what weak interaction can mean in practice. The LHC produces enormous numbers of neutrinos, yet the general-purpose detectors around the collision points were not built to record most of them directly. Specialized experiments such as phasor and SND at the LHC were placed in locations where particles traveling along or near the beam direction could be studied in ways the large detectors cannot easily provide. That same logic can be extended to hypothetical particles. Some theories contain a hidden sector, a collection of particles that interacts only faintly with the particles of the standard model. A dark photon, a heavy neutral lepton, or another weakly coupled particle could be produced and travel a considerable distance before interacting or decaying. If the coupling is weak enough, producing fewer clean collisions is not necessarily the only problem. The geometry of the detector matters. The direction of travel matters. The lifetime matters. A particle can pass through the part of the experimental world that was designed for another signal pattern. This is why CERN's search program extends beyond ATLAS and CMS. Phaser looks for light and extremely weakly interacting particles traveling forward from LHC collisions. NA64 searches for hypothetical dark sector particles using a beam directed at a fixed target. And the planned SHEEP experiment is designed specifically to search for very feebly interacting and long-lived particles using CERN's accelerator complex in a different way. The existence of these experiments is a useful reminder that a collider is not a single pair of giant detectors. It is an ecosystem of instruments, each sensitive to a different part of the possible world. The third hiding place concerns lifetime. When we imagine a particle collision, it is natural to picture the new particles appearing at the collision point and decaying almost immediately. That is how many familiar heavy particles behave, and much of traditional collider reconstruction is built around that geometry. But a new particle might live longer, though not long in the ordinary sense. It may survive for a tiny fraction of a second and still travel millimeters, centimeters, or meters before decaying because it is moving so quickly. That small delay changes the appearance of the event. The decay products may emerge from a point displaced from the original proton collision. A charged particle may leave part of a track and then seem to vanish. A neutral particle may cross several layers of a detector before suddenly decaying in a region where ordinary searchers do not expect a new shower of particles. ATLAS has developed dedicated strategies for these long-lived signatures because assuming that everything originates at the collision point creates a blind spot. The compressed supersymmetry searches we just visited offered one example. Very short disappearing tracks required new reconstruction methods because the conventional algorithms expected more detector hits. Other long-lived particle searches look for displaced vertices, delayed signals, or unusual deposits of energy far from the center of the detector. The physics could therefore be accessible in energy and still difficult to see because the event does not resemble the events the experiment was originally optimized to recognize. This is one of the quieter lessons that comes from years of null results. The experiment learns where a particle was absent and which assumptions made that absence meaningful. If a search assumes prompt decay, it constrains prompt decay. If another search is designed for long lifetimes, it can test a different region. Together, those searches cover more of the territory without pretending that any one analysis covers all of it. A fourth possibility is that the missing physics may not present itself as a new particle produced in a high-energy proton collision at all. Dark matter gives us the clearest reason to keep this possibility open. Its existence is inferred from gravitational effects across galaxies and clusters, but the identity of the dark matter is still unknown. Some candidates could be produced at colliders. Others are better approached through underground detectors, waiting for dark matter to scatter from ordinary nuclei, through telescopes looking for possible products of dark matter interactions in space, or through laboratory experiments searching for extremely weak fields and particles. The same broader strategy appears at CERN itself. In 2026, CERN began developing a long-term roadmap specifically for non-collider physics. The program includes experiments that use fixed targets, antimatter, precision measurements, neutrinos, and searches for particles that interact too feebly for the main collider detectors. That does not mean colliders have reached the end of their usefulness. The LHC remains one of the most sensitive tools ever built for testing fundamental physics, and its high luminosity upgrade will greatly increase the amount of data available for rare processes and precision studies. It means something more modest. That wider program matters because some proposed particles and mechanisms would be easier to test with instruments other than a proton collider. A missing particle could be too heavy, light but almost disconnected from ordinary matter, able to decay in an unexpected place or after an unexpected delay, or part of a phenomenon better approached through a completely different kind of experiment. These possibilities are not predictions that one of them must be correct. They are categories of remaining uncertainty, and each category carries different experimental consequences. That distinction matters because the silence of the LHC becomes easier to misinterpret as the searchers grow more sensitive. If a detector was sensitive to a particular signal and the signal did not appear, that possibility has genuinely lost ground. But the conclusion stops at the boundary of the search. It does not extend automatically to particles heavier than the accessible range, interactions too weak for the detector, lifetimes the analysis was not designed to recognize, or phenomena that do not belong to collider production in the first place. The central change is that the missing physics began as something CERN had not found yet, while the accumulated measurements have turned that vague absence into a more precise set of possibilities. Years of searches have removed many of the easier possibilities. Better measurements have weakened several famous anomalies. Antimatter has behaved more normally than some dramatic alternatives would have required. And the astronomical problems that tell us the theory is incomplete have not gone away. So the unknown remains, but it cannot be placed anywhere we like. Every sufficiently sensitive null result removes another place where a particular answer could have been. What is left may be rarer, weaker, stranger in its experimental signature, or farther away in energy than the early hopes suggested. And that last possibility leads to a limit that no amount of patient data collection can completely avoid. Every collider has an energy horizon. At a collider, that horizon comes from two forms of reach that are easy to confuse. One kind of reach comes from the collision energy, and the other from how many useful collisions the machine can produce. The two are related, but they are not interchangeable. During Run 3, the Large Hadron Collider brought proton beams together at a center of mass energy of 13.6 tera-electron-volts. That is the energy of the two proton beams combined in a head-on collision. It is an enormous number by laboratory standards, and it makes the LHC the highest energy collider that has ever operated. But even that number needs one more layer of explanation. A proton is not elementary, and inside it are quarks and gluons, continually sharing its momentum in a complicated quantum system. When two protons collide, the hard interaction that produces a heavy new object usually happens between one constituent from one proton and one constituent from the other. Those constituents carry only part of the energy of the full proton beams. So a 13.6 tera-electron-volt proton collision does not mean that every individual particle-producing interaction has 13.6 tera-electron-volts available to build something new. Many interactions have much less, while rarely two constituents may carry unusually large fractions of their parent proton's momentum, giving the collision access to very high masses. But as the mass of the object you are trying to produce increases, the collisions capable of producing it generally become less common. This produces a boundary that is softer than a wall, but just as important experimentally, because a light new particle might appear often while a heavier one may emerge only in rare collisions. Push the required mass still higher, and eventually the useful collisions become so scarce, or the energy becomes insufficient, that direct production fades out of practical reach. Collecting more data helps while the process is rare but still accessible. If a signal is exceedingly rare but still accessible, then producing many more collisions gives you more chances to see it. If the signal requires an energy your machine cannot provide, waiting longer does not solve the problem. This is the distinction between the luminosity frontier and the energy frontier. Luminosity gives you more attempts, while energy allows different things to happen in those attempts. The Large Hadron Collider has already spent years moving along both directions, although not equally. Its collision energy increased between its early runs, allowing searchers to reach heavier states and changing the production rates of many known processes. At the same time, the machine accumulated larger datasets, allowing experiments to study increasingly rare processes and measure known particles with greater precision. The next phase, the high-luminosity LHC, is deliberately weighted toward the second kind of improvement. Its name tells you what CERN is trying to gain: luminosity. The upgraded machine is designed to produce far more collisions over its lifetime than the original LHC program. That matters enormously for Higgs physics, rare decays, precision measurements, and searches for weak signals that may already lie within the collider's accessible energy range. But the upgrade does not turn the 27-kilometer ring into a radically higher energy collider. The LHC was designed for proton collisions reaching up to roughly 14 teraelectron volts, and the high luminosity program is built around extracting much more information from essentially that energy regime. This is why calling the upgrade a radically higher energy collider can create the wrong picture. It will be more capable as a scientific instrument because it will deliver much larger samples of collisions, and improved detectors will record them in greater detail. But it will not suddenly open an entirely new energy continent. If the missing physics lies just beneath the noise, luminosity may reveal it. If it appears through a decay that occurs once in an enormous number of events, luminosity may reveal it. If a subtle deviation in the Higgs boson becomes visible only after millions of Higgs particles have been measured, luminosity may reveal it. If a hypothetical particle is far too massive to be produced at these collision energies, luminosity alone cannot bring it into existence. That is the energy horizon, and it is no more mysterious than the limits of other scientific instruments. A telescope has wavelengths and brightness levels it can detect. A microscope has a finite resolution. A neutrino detector has useful ranges of energy and interaction rate, and a collider has boundaries set by collision energy, luminosity, detector acceptance, and other practical constraints. The uncomfortable part is that nature is under no obligation to place the next fundamental discovery inside them. For decades, particle physics benefited from a remarkable sequence in which higher energy machines repeatedly opened new territory. As accelerators became capable of producing new particles, the W and Z bosons were found, then the top quark, and eventually the Higgs boson. That history makes it natural to imagine a staircase where the next larger collider reveals the next layer, followed by another collider and another layer after that. Nature may still work that way, but the standard model itself does not tell us that it must. The unresolved questions do not come with a label saying how much energy is needed to solve them. Dark matter could involve particles accessible near the electroweak scale, which is one reason collider searches have been so important. Or the relevant particles could be much heavier. Neutrino masses could be generated by physics at comparatively low energies, potentially leaving signatures within reach of experiments. Or the mechanism could involve scales vastly beyond direct collider production. A deeper quantum description of gravity is expected to matter under conditions far removed from ordinary particle collisions, and no established theory tells experimentalists that a quantum gravity particle must conveniently appear at the LHC. The evidence says the known framework is incomplete without telling us how far away a deeper description sits, and that uncertainty changes the meaning of building a larger machine. A higher energy collider would not guarantee discovery. It would open territory that has never been searched directly, which is a different promise. In May of 2026, the updated European Strategy for Particle Physics reaffirmed the high luminosity LHC as Europe's highest medium-term priority and recommended an electron future circular collider, known as FCCE, as the preferred option for CERN's next flagship collider. The proposed machine would use a tunnel around 91 kilometers in circumference, more than 3 times the length of the current LHC ring. Its first stage would not chase the highest possible collision energy. Instead, electrons and positrons would collide in a much cleaner environment than protons, allowing extremely precise measurements of particles such as the Higgs boson and the Z boson. This may sound like a retreat from the energy frontier, but it reflects another way of searching when new particles refuse to appear directly. If very heavy physics cannot be produced, it may still leave tiny fingerprints on familiar particles. The Higgs boson is particularly useful for this because its interactions are connected to some of the deepest open questions in particle physics. Measure those interactions with enough precision, and a small deviation could reveal the influence of something too heavy to create directly. The proposed FCC program also preserves a second possibility for the much more distant future. The same large tunnel could potentially be reused for a proton-proton collider operating at much higher energies than the LHC, with designs discussing collision energies reaching up to around 100 tera-electron-volts. That would move the energy horizon dramatically, but 100 tera-electron-volts would still leave heavier masses beyond direct production, interactions too weak to reveal themselves easily, and questions that no collider alone could answer. This is worth lingering on because it prevents the story from turning into a simple sequence of ever larger machines. There is no known accelerator size at which physicists can say that all possible new fundamental physics must finally become visible. Increasing energy expands the territory, increasing luminosity examines accessible territory more thoroughly, and increasing precision can reveal the indirect influence of physics beyond direct production. Different experiments explore different signatures, so together they reduce ignorance without placing a final wall around nature. The engineering itself also makes that clear. In a circular accelerator, charged particles want to travel in straight lines. Magnets bend them back around the ring. As particle energy rises, stronger magnetic fields are needed to keep the beam on the same curved path. Greater energies can be reached with stronger magnets, or with a larger ring that bends the beam less sharply, and both approaches encounter practical limits in materials, technology, power, construction, and cost. This is why the history of accelerators has also been a history of larger machines and new magnet technologies. The limit is not a single equation saying humanity may go no farther. It is the point where the physics goal, engineering possibilities, and resources available have to meet. That makes the energy horizon a human boundary, as well as a physical one, because we can imagine energies far beyond anything we can currently create in a laboratory, even though the early universe reached them naturally. Cosmic rays still strike Earth's atmosphere with individual particle energies far beyond those routinely produced by our accelerators, although those collisions arrive unpredictably and cannot replace a controlled collider program. The early universe and the highest energy cosmic rays reach conditions beyond our controlled accelerators. Our machines create smaller, repeatable versions of extreme conditions and surround them with detectors we can understand. That control is what makes the measurements scientifically useful. It is also what defines their range. So when the standard model continues to survive, there are at least two very different interpretations that remain possible. Perhaps the new physics is close, and the next improvement in precision or statistics will expose a tiny deviation that has been hiding in the data. Or perhaps some of the important new physics lives much farther away in energy, leaving only subtle traces at the scales we can reach. Current experiments cannot choose between those possibilities in advance, so they keep narrowing them, which brings us back to the machine now sitting silent beneath France and Switzerland. CERN is not responding to the absence of a dramatic discovery by immediately abandoning the LHC for a larger ring. The next step keeps the same tunnel and changes the basic collision energy relatively little, while preparing the experiments to collect far more information from territory they can already reach. Before asking nature a much more energetic question, CERN is going to ask the present question many more times. Doing that requires an upgrade built around collision statistics rather than a dramatic jump in beam energy. That may sound almost too simple for an upgrade that requires years of work underground, new magnets, redesigned detectors, new electronics, new computing systems, and the replacement of large sections of the accelerator. But the central idea behind the high-luminosity Large Hadron Collider is remarkably straightforward. The LHC has already shown physicists what can be learned at its present energy range. Now they want much more data from that range. In collider physics, luminosity describes how many potential particle collisions an experiment receives. A machine with higher luminosity gives physicists more opportunities for rare processes to occur. Integrated luminosity measures that opportunity accumulated over time. The difference is a little like watching the night sky for a rare meteor. A brighter telescope cannot make the meteor appear, and watching for 1 minute may tell you very little. But if the event happens occasionally, and you watch the same region night after night, with an instrument capable of detecting it, your chances of recording one increase. Particle physics is more complicated than that, but the statistical idea is similar because some processes at the LHC happen constantly while others are far rarer. The Higgs boson is already rare compared with the enormous number of ordinary proton interactions taking place inside the machine. Some particular Higgs decays are rarer still. If new physics alters one of those uncommon processes only slightly, the effect may remain hidden inside statistical uncertainty until the experiments have collected a very large sample. More collisions matter because they make those comparisons sharper. The high luminosity LHC is designed to increase the total amount of collision data delivered over its lifetime by roughly a factor of 10 compared with the original LHC design goal. That additional data changes which questions can be asked with useful precision. Imagine measuring a coin that you suspect is very slightly biased. With a small sample, a slight imbalance means very little. With a much larger sample, the uncertainty shrinks and a tiny persistent imbalance becomes much harder to dismiss as chance. At CERN, the same statistical logic applies across particle processes governed by quantum probabilities. Physicists measure how often particles are produced, how they decay, the angles at which decay products leave, how much momentum they carry, and how those distributions compare with theoretical calculations. More data makes those comparisons sharper. The Higgs boson will be one of the clearest beneficiaries. Since its discovery in 2012, ATLAS and CMS have gradually measured more of its properties. The experiments have observed several of the ways it is produced and several of the ways it decays. They have tested its interactions with other known particles, and so far, the overall picture has remained consistent with the standard model. But there are still important Higgs interactions that are difficult to measure precisely. One of the most interesting involves the Higgs interacting with itself. The Higgs field has a particular shape in the standard model, and that shape is connected to the way the early universe changed as it cooled. Measuring the Higgs self-interaction therefore tells physicists something deeper than the mass of one particle. One way to approach it is to look for events in which two Higgs bosons are produced together. Those events are extremely rare at the LHC. A much larger dataset gives ATLAS and CMS more chances to collect them. Even then, measuring the Higgs self-coupling precisely will remain difficult. High luminosity supplies a larger sample for a rare process, making a serious measurement more practical without making the process common. The same logic applies to searches beyond the standard model. Suppose a new particle can be produced at current LHC energies, but only rarely because its interaction with ordinary particles is weak. The present dataset might contain too few examples to separate a signal from background. With substantially more collisions, the number of possible signal events could grow enough for a pattern to emerge. Or suppose no new particle appears directly, but some heavy hidden physics changes a familiar decay probability by a small amount. In that situation, improved precision becomes the way the experiment detects the indirect effect. The machine is still colliding protons at roughly the same fundamental energy scale, but the experiment becomes sensitive to smaller deviations. The high luminosity LHC therefore explores a different dimension of the problem. Its collision energy sets the range available for direct production, and its much larger data sample lets physicists study accessible processes more deeply. Gaining that luminosity requires major changes to the accelerator during the present long shutdown. More than 1.2 kilometers of the LHC are being dismantled and replaced with new systems. Near the ATLAS and CMS collision points, new superconducting magnets will help squeeze the proton beams more tightly before they cross. When more protons are concentrated into the collision region, the probability of interactions increases. A technology called crab cavities will also help. The two beams do not meet as perfectly overlapping cylinders. They cross at an angle. Crab cavities use radio frequency electromagnetic fields to tilt the particle bunches immediately before the collision, so that they overlap more effectively. The name comes from the sideways appearance of the bunch rotation, a tiny and extraordinarily precise motion designed to bring more protons into useful contact. Increasing the number of collisions then creates a second problem, because the detectors have to survive and understand the denser environment. ATLAS and CMS were already built to operate in an environment filled with overlapping proton interactions. The high-luminosity LHC will make that environment much denser. Many proton collisions can occur within the same crossing of the beams. Their particles travel through the detector at nearly the same time, leaving layers of tracks and energy deposits that have to be separated computationally into different interaction points. This overlapping activity is called pileup, and it becomes more severe at higher luminosity, so the experiments themselves have to be rebuilt along with the accelerator. CERN expects roughly 140 to 200 proton-proton collisions each time the bunches meet at the heart of ATLAS and CMS in the high-luminosity era, compared with around 60 collision events under current LHC conditions. That density changes what reconstruction has to accomplish. Tracks from many separate interactions arrive inside the same narrow time window, so the upgraded detectors need finer tracking, improved timing, and faster electronics to decide which pieces belong together. The extra data are useful only if the experiments can separate that crowded event environment well enough to recover the rare process hidden inside it. CMS is receiving an entirely new tracking detector. ATLAS is replacing major components as well. New electronics, timing systems, and trigger technologies will help both experiments decide which events to record and how to reconstruct them in an environment containing far more simultaneous information. The detectors are becoming better because the experimental conditions are about to become much harder, even though the known particles themselves have not changed. There is a useful symmetry in that. CERN wants sensitivity to faint signals, so the machine creates more collisions, but those collisions also create more background and more overlapping tracks, which means the detector must become better at separating one event from another. Every gain produces another problem that has to be solved before the gain becomes scientifically useful. That is why long shutdown 3 lasts years rather than months. By mid-2026, the collider itself had stopped producing physics data, and CERN's underground facilities had become construction sites. Equipment that had operated for more than a decade was being removed. New infrastructure was moving toward installation. ATLAS and CMS were opening parts of detectors that are normally inaccessible during operation. The silence of the collider does not mean CERN has become quiet. For several years, much of the work happens without collisions at all. Then, around 2030, according to CERN's current schedule, the high-luminosity era is expected to begin. If everything works as planned, the experiments will accumulate a dataset far larger than anything available today. CERN estimates that the high-luminosity program could produce about 380 million Higgs bosons over its lifetime. That larger sample is especially useful when a rare decay or production channel leaves only a small fraction of events after detector acceptance and analysis selections are applied. That number sounds enormous until we remember that the experiments divide Higgs events by production process, decay channel, detector acceptance, and analysis requirements, rather than treating every Higgs boson as part of one usable sample. A sample that begins with millions can become surprisingly small when physicists ask for one particularly rare signature. The extra collisions matter because particle physics spends data very quickly. Greater precision, rare processes, and strict selections used to control backgrounds all consume events, so a signal living in a tiny corner of the data can require an enormous starting sample. The high-luminosity LHC is designed to provide that sample. But it is important not to give the upgrade a promise it cannot keep. More collisions do not guarantee a new particle, supersymmetry, a collider explanation for dark matter, or a solution to the matter-antimatter problem, and they do not extend direct particle production to arbitrarily high masses. The machine can become much more sensitive and still find that the standard model describes every accessible measurement within experimental uncertainty. That outcome would still be scientifically meaningful if the Higgs continued behaving as expected, rare decays remained within standard model predictions, long-lived particle searches became more sensitive without finding a signal, and collider-accessible dark matter candidates lost further portions of their parameter space. Further null results could constrain more of the accessible parameter space. And if that happens, the absence would become harder to dismiss as a simple consequence of insufficient data. One striking difference in the high luminosity program is that the original LHC began with a clear missing piece inside the standard model, the predicted but unobserved Higgs boson, and the machine found it. The next search has no single agreed particle waiting at one known mass. There are families of theories, ranges of possibilities, indirect effects, and cosmic mysteries pointing outward in different directions. So the upgraded collider is not approaching a door for which physicists already possess the key. The upgraded collider will examine familiar processes more carefully, and either a persistent opening or another stretch of agreement will change what can reasonably be believed about the physics beyond them. Precision helps by making ordinary measurements exact enough that a hidden difference has fewer places to remain unnoticed. When the collider begins running again, CERN will have more collisions, better detectors, and much greater sensitivity to rare events. But the question beneath all of that engineering will remain the one we have been carrying since the ring went quiet. If the missing physics is real, how much smaller can its hiding place become before our idea of where to look has to change? By now, the map we have been drawing looks very different from the one physicists had when the Large Hadron Collider first began operating. At the beginning, many possibilities were open at once. New particles might have appeared almost immediately above the energies explored by earlier accelerators. Supersymmetric partners might have been light enough to produce in large numbers. A dark matter candidate might have left a recognizable imbalance in the detectors. Rare particle decays might have departed clearly from standard model predictions. Precision measurements might have exposed a disagreement that grew stronger as the uncertainties became smaller. Some of those possibilities are still alive in modified forms. Others occupy much less space than they once did. This is difficult to visualize because the map is not a map of physical locations. There is no hidden valley beneath Switzerland where supersymmetry can retreat, and no distant island where a dark matter particle waits beyond the horizon. The coordinates are properties. Mass can be one coordinate, interaction strength another, with lifetime decay probability mixing angle or coupling providing others. A theory with several unknown quantities therefore describes an entire collection of possible universes, each produced by choosing different values for those quantities. Physicists call that collection a parameter space. The name is dry, but the idea is simple if you imagine being told that an unknown object is somewhere in a dark room, with almost every location possible at the beginning. You search one corner and find nothing. The object could still exist, but if your search would have detected it there, that corner is no longer a reasonable hiding place. You continue beneath the table, behind the door, and inside a cabinet, and each careful search removes another ordinary location. After several empty searches, the object may still exist elsewhere, while the locations you examined become less plausible. There are fewer ordinary hiding places left. Particle physics works in a similar way, except the room may have many dimensions and the searchlight changes from one experiment to another. Atlas may exclude combinations of mass and lifetime for one hypothetical particle. CMS may test a related model through a different decay signature, and LHCb may constrain new interactions through beauty particle decay. Antimatter experiments test gravity and spectroscopy. Underground detectors search for dark matter scattering. Astronomers look for possible dark matter signals in the sky. And neutrino experiments probe the origin of neutrino mass, so each instrument illuminates a different region. The regions do not fit together perfectly, because each conclusion depends on assumptions. A particle excluded under one decay pattern may remain possible if it decays differently. A dark matter candidate invisible to one detector may still be accessible to another. A heavy particle beyond direct production may still influence precision measurements indirectly. So the map never becomes a simple picture with the unknown squeezed into one last dot. It becomes a layered collection of boundaries. Some boundaries are strong, some depend heavily on the model, some overlap, and others leave wide open regions between them. But compared with the beginning, the freedom is smaller. That is one of the great changes produced by a long period without a spectacular discovery. As those constraints accumulate, theories have to fit through narrow experimental gaps, which changes the searches that come next. Consider what has happened to some of the ideas we have already followed. Simple supersymmetric scenarios that would have produced abundant new particles at accessible masses have been tested repeatedly. Many of those versions are now excluded across substantial regions of their parameter spaces. Compressed scenarios remain more difficult, so experiments have developed methods for very soft particles and disappearing tracks. Long-lived particles remain possible in many models, so searchers now look for decays far from the original collision point. Weakly interacting particles may escape the central detectors, so experiments such as phasor explore different geometry. Particles too heavy for direct production may still alter precision measurements, so physicists study familiar particles more carefully. Every time the search adapts, it is responding to the shape left by earlier searches. Earlier null results therefore determine which signatures later searches prioritize. This is easy to overlook if we describe every experiment as another attempt to find the same missing thing. It is not. The experimental program evolves. A search in 2026 is not merely the same search performed in 2016 with a larger pile of collisions. The detectors and reconstruction methods have improved, while new signatures have become important. Some theoretical ideas have lost motivation, while others have moved toward regions that earlier analyses barely touched. The unknown itself has become experimentally more complicated, and when an anomaly disappears, the map does not return to its previous state. The flavor anomalies provide a good example. When measurements suggested that beauty particles might treat electrons and muons differently, theorists explored models capable of producing that pattern. Those models connected a very specific experimental tension to particular kinds of new interactions. When the improved LHCb measurement moved back toward lepton universality, that route became less compelling, even though the matter-antimatter problem, dark matter, and neutrino masses remain. A precise W boson measurement that agrees with the standard model has the same effect. The broader need for deeper physics survives, while one convenient bridge toward it becomes less secure, giving experimental silence a measurable structure. A perfect absence would tell us nothing if the experiment had no sensitivity. But once an instrument becomes capable of detecting a certain effect, the absence of that effect becomes part of our knowledge. The distinction is essential. If you look into the night with your eyes and fail to see a distant galaxy, you have learned almost nothing about whether the galaxy exists. If a telescope known to detect galaxies of that brightness at that distance surveys the same region carefully and still finds nothing, the statement becomes more meaningful. The absence has been calibrated, and particle experiments spend enormous effort doing that by measuring detector efficiencies, estimating backgrounds, testing reconstruction methods, simulating signals, and comparing control regions where known processes should dominate. Only after understanding what the experiment could have seen can they say something useful about what was not there. That discipline is what turns empty space on a graph into evidence. And as the evidence accumulates, an interesting asymmetry appears between what we know and what we do not know. We know the standard model works extraordinarily well across the energies and processes where it has been tested. We know neutrinos have mass. We know galaxies and galaxy clusters contain gravitational effects that visible matter alone does not explain. We know the observable universe is dominated by matter rather than antimatter. We know gravity is not contained within the standard model's quantum description of the other interactions. Those statements are strong. What is weak is our ability to connect them to one confirmed new microscopic mechanism. We do not know the dark matter particle, assuming dark matter is made of particles at all. We do not know the mechanism that generated the cosmic matter excess, the full origin of neutrino mass, or how gravity fits into a quantum description of fundamental physics. And after years of collider searches, we have fewer simple ways to pretend that we do. There is something almost reassuring about that once the disappointment is removed. Science has reached a stage where ignorance is more precise. Some combinations of particle mass and interaction strength conflict with observations, Some proposed deviations have failed to survive improved measurements, and some dramatic alternatives for antimatter have become tightly constrained. Any new phenomena that remain may be rarer, weaker, heavier, or experimentally less obvious than the versions already tested. The question has acquired borders, and borders change how you explore because almost any direction feels reasonable when an entire continent is unknown. Once coastlines have been measured, mountains located, and large regions surveyed, the remaining blank spaces demand more deliberate expeditions. That may be where fundamental physics is now. The high-luminosity LHC could reveal an unexpected particle or a persistent deviation. A precision experiment could find a difference that refuses to disappear. A dark matter detector could register a reproducible signal. A neutrino experiment could uncover a new source of CP violation. Or a future collider could open an energy range where unfamiliar particles become accessible. None of those outcomes is guaranteed, yet the search remains meaningful because theories can become less plausible, regions can close, measurements can sharpen, and explanations can lose their easiest versions, while the central question remains unanswered. That is progress of a kind that is almost invisible from outside science, because nothing new has appeared. A mature scientific mystery can begin with many possible answers, and then survive while evidence removes some of them, leaving the remaining question less free to take any shape we want. Beneath France and Switzerland, the Large Hadron Collider is now being rebuilt so that it can return to the same territory with far more sensitivity. Above it, the universe continues to display the same unanswered clues that motivated the search in the first place. Galaxies still carry unseen gravity, neutrinos still carry tiny masses, matter still fills a universe that might easily have contained far less of it, and gravity still curves space-time without fitting into the quantum framework used for the other forces. And between those facts and the particles we have already found lies a map with more borders than it had earlier in the LHC program. The untested regions are still wide, but they are no longer interchangeable with regions the experiments have already examined. That distinction is what the quiet ring carries into its shutdown, because when the machine returns, it will not be starting the search from the beginning. The ring beneath France and Switzerland is quiet now, at least in the sense that no proton beams are circling through it, and no new physics collisions are filling the detectors with fresh events. The last physics collisions ended on June 14, 2026, and CERN then spent 2 more weeks testing high-intensity beams before the final beams were dumped on June 27. Since then, the LHC has become a construction site, with sections of the accelerator opened, equipment removed, and the long work of turning the machine into the high-luminosity LHC moving underground. For years, that 27-kilometer tunnel carried beams around its ring, while Atlas, CMS, LHCb, and the other experiments recorded the traces left by the collisions. Now, magnets are being replaced, detector systems are being opened, electronics are being redesigned, and sections of accelerator hardware are being dismantled and renewed. The machine built to study the smallest pieces of nature has entered a period dominated by cables, vacuum systems, superconducting magnets, sensors, timing electronics, and the patient engineering needed to make the next period of measurement possible. The question waiting for the machine has changed during the years it has been operating. The standard model still describes the known particles and 3 fundamental interactions with extraordinary success, yet gravity remains outside that framework. Neutrino masses require an extension of its simplest form, the gravitational evidence for dark matter remains, and the universe still contains far more matter than the known sources of CP violation can readily explain. None of this means the standard model has stopped working. Its proven domain remains narrower than the full set of facts a deeper theory still has to explain. The LHC did resolve one famous missing piece. In 2012, Atlas and CMS found the Higgs boson, turning a particle that had been predicted for decades into something that could be measured directly. The search beyond the standard model has unfolded differently. Many hypothetical particles that would have produced clear signals in particular mass ranges have not appeared there. Compressed, supersymmetric scenarios have been tested with increasingly sensitive reconstruction. Long-lived particles have been sought through displaced or disappearing tracks. And precision measurements have revisited tensions that once looked more suggestive than they do now. Antimatter has given the same story another form. Alpha released anti-hydrogen in Earth's gravitational field and found behavior consistent with ordinary downward gravity within the precision of the experiment. Its spectroscopy has become dramatically more precise without revealing a forbidden difference between hydrogen and anti-hydrogen. LHCb, meanwhile, observed CP violation of baryon bond decay for the first time, extending a real matter-antimatter asymmetry into a new class of particles while leaving the much larger cosmic imbalance unexplained. Each result adds information, even when it does not provide the missing mechanism. This is where sensitivity becomes as important as discovery. An empty search is weak evidence, when an instrument would not have been able to see the proposed signal anyway. Once an experiment is demonstrably sensitive to a particular mass, lifetime, interaction strength, or decay pattern, the absence of that signal becomes a constraint on that part of the model. The conclusion remains conditional, because a different lifetime, a weaker coupling, a heavier particle, or a different production mechanism can move the possibility somewhere else. But the region that was actually tested no longer has the same freedom it had before. That is what the long sequence of null results has produced. Not one final answer, but a more detailed boundary around many possible answers. The accumulated constraints are uneven. Supersymmetry remains a broad framework, though many specific scenarios occupy less parameter space. Dark matter is still unidentified, and collider searches now rule out particular signatures rather than the astronomical phenomenon itself. Several prominent measurement discrepancies have also become less persuasive after improved data and analysis, while leaving other routes to new physics open. No single experiment reaches the whole unknown. Across the wider program, however, the combined measurements define its experimentally allowed forms more tightly than before. When the high-luminosity LHC begins operating around 2030, CERN will return to much of the same energy range with a far larger statistical sample and upgraded detectors built for a denser collision environment. The Higgs boson will be measured more carefully, rare processes will have more opportunities to occur, and searches for faint or unusual signatures will gain sensitivity. If a small deviation is already hiding within the accessible energy range, the larger dataset may make it easier to separate from background. If the measurements continue to agree with the standard model, the remaining explanations will have to fit within narrower experimental limits. That still leaves the energy horizon. More collisions can expose rare processes that the machine is already capable of producing, but they cannot create a particle whose mass lies far beyond the available collision energy. A future collider could move that horizon, and the proposed future circular collider would open a different precision program first, and potentially a much higher energy proton program later. Even then, a larger machine would explore more territory rather than guaranteeing a final theory, because nature can place relevant physics at higher masses, weaker couplings, longer lifetimes, or in phenomena that are better approached by another experimental method. So the search now extends well beyond one ring. Phaser and SND at the LHC explore weakly interacting particles and neutrinos in directions the main detectors do not cover well. NA64 searches for dark sector particles with a fixed target. SHEEP is planned to study very feebly interacting and long-lived particles. Antimatter experiments test gravity and spectroscopy. Neutrino experiments probe the origin of neutrino mass and possible asymmetries. Underground detectors wait for rare dark matter interactions, and astronomical observations continue mapping the gravitational effects that created the dark matter problem in the first place. For now, all of those approaches coexist with the quiet collider. Beneath ordinary roads, farms and towns along the French-Swiss border, the beam pipes are empty and the detector caverns are open for work. While above them galaxies continue to turn inside halos of unseen mass, neutrinos pass through the planet almost unnoticed, matter fills stars and living bodies, and gravity curves the space-time around them. Our equations describe an extraordinary amount of that world, and the parts they do not explain are now surrounded by more measurements than they were when the LHC first switched on. Until the beams return, the unfinished map remains there with the ring, carrying the boundaries of the places that have already been searched, and the open regions that the experiments have not yet reached.